Example 4.7. Consider the neutral hydrogen atom. Estimate using the time-averaged potential. See the next equation, where Q is the magnitude of the electronic charge, alpha to the -1 power equals half the Bohr radius. Find the distribution of charge, both continuous and discrete. Solution. First, to get the discrete distribution, notice that as r goes to 0 we get lim over r goes to 0 of phi equals Q over r. From the definition of the Dirac delta function, see the equation shown.
We get -4 pi rho equals gradient squared phi equals -4 pi q delta of r goes to rho equals q delta of r. Thus, we have a point charge of q at r equals 0, which corresponds to the positively charged nucleus consisting of the point particle, at this energy scale, of the proton. Let's now consider the continuous part, which has only a radial dependency thus. See the next equation. Thus, see the equation shown. The total charge in the continuous distribution is. See the next equation. The continuous distribution has total charge -q, the electron cloud, with negative charge corresponding to 1 electron.
Example 4.8. Calculating capacitance for various geometries. Recall the capacitance relation. Q equals CV, that results from the definition that two conductors with a potential difference of V and a charge of Q on one, but matching opposite. Using Gauss's law, compute the capacitance for the following scenarios. A. Two large flat sheets of area, A, separate by D, where D is much less than the square root of A, so we can ignore edge effects and are approximate using an infinite plane. The E field near an infinite plane is 4 pi sigma. The potential near an infinite plane, thus, only changes as you move away from the plane. E equals negative gradient phi goes to phi equals 4 pi sigma x, where the I've chosen x as the dimension separating the two planes. Thus, the potential difference between the two planes separated by x equals d will be phi equals 4 pi sigma d. The charge on one plate is a sigma, so the capacitance is.
See the equation shown. B. Two concentric conducting spheres with radii a, b. From previous results we know inside the innermost conducting sphere we have E equals 0, and the same is true outside the outer sphere, since the charge enclosed by the enveloping sphere is 0. So, only between the spheres we have. See the next equation. The potential difference is V equals Q over A minus Q over B equals Q, B minus A over A, B, while the charge is Q equals Q, so. See the equation shown. C. Two concentric conducting cylinders, radii A, B of length L. With L is much greater than B is greater than A is less than R is less than B. See the next equation.
See the equation shown. The difference in potential between the cylinders is then. See the next equation. And C equals Q over V equals L over 2 natural log of A over B. Example 4.9. Consider two long cylindrical conductors, with radii A, B, separated by distance d is much greater than B is greater than A. For each cylinder we have. See the equation shown. Thus, the potential at each cylinder. See the next equation. See the equation shown. The capacitance of the system is thus. See the next equation.
Example 4.10. For the capacitor geometries of Example 4.8, ABC, get the total electrostatic energy and show W equals 1/2 QV. Recall W equals 1 over 8 pi the integral of the absolute value of E squared of d cubed x. A. For parallel plates. See the equation shown. B. For concentric spheres, the absolute value of E equals Q over R squared and. See the next equation. And since. See the equation shown. We get. See the next equation. C. For concentric cylinders, the absolute value of E equals 2Q over LR and. See the equation shown. And since.
See the next equation. We get. See the equation shown. Example 4.11. Calculate attractive force between conductors 4. Example 4.8. A. The parallel plates. A. For parallel plates separated by distance x we have. See the next equation. Example 4.12. Prove the mean value theorem of electrostatics. The mean value theorem of electrostatics states that for charge-free space, the value of the electrostatic potential at a point is the same as the average of the electrostatic potential on a sphere centered at that point. We have, from the divergence theorem, see the equation shown. Let a vector equals phi gradient psi. See the next equation. To arrive at Green's theorem,
see the equation shown. And the integral over v of phi gradient squared psi minus psi gradient squared phi equals the integral on contour S of phi the partial derivative of psi with respect to n dA minus psi the partial derivative of phi with respect to n dA. Let gradient squared psi equals negative 4 pi delta x minus x prime equals gradient squared 1 over r psi equals 1 over r for a unit point charge and phi equals phi of x prime, such that gradient squared phi equals negative 4 pi rho of x prime.
See the next equation. Or, see the equation shown. See the next equation. Example 4.13. Use Gauss's theorem to prove that at the surface of a charged conductor with principal radii of curvature r sub 1 and r sub 2 has normal derivative of its electric field given by. See the equation shown. Starting with Gauss's theorem, see the next equation. And since dA equals r sub 1 r sub 2 d theta sub 1 d theta sub 2, see the equation shown.
Note that. See the next equation. Thus, 1 over e the partial derivative of e with respect to n equals 1 over 4 pi dq over r sub 1 r sub 2 d theta sub 1 d theta sub 2 times negative 4 pi dq over r sub 1 squared r sub 2 d theta sub 1 d theta sub 2 plus negative 4 pi dq over r sub 1 r sub 2 squared d theta sub 1 d theta sub 2 equals negative 1 over r sub 1 plus 1 over r sub 2.
Example 4.14. Prove Green's reciprocation theorem. See the equation shown, where we have two specifications of potential and charge on a given volume V with surface S. Recall the second form of Green's theorem. See the next equation. Let phi equals phi and psi equals phi prime. Then gradient squared phi equals negative 4 pi rho and gradient squared psi equals negative 4 pi rho prime, and recall that sigma equals 1 over 4 pi the partial derivative of phi with respect to n. See the equation shown. Thus we get the desired result. The integral over v of rho phi prime d cubed x plus the integral over s of sigma phi prime dA equals the integral over v of rho prime phi d cubed x plus the integral over s of sigma prime phi dA.
Example 4.15. Consider two infinite, grounded, conducting planes separated by d. A point charge q is placed between the planes, distance x prime from one plate. Show induced charge is negative qx prime over d at other plate. Starting from Green's reciprocation theorem. See the next equation. And choosing prime case with charge only on surface, phi prime equals 4 pi sigma prime x prime and rho prime equals 0. See the equation shown. And see the next equation. Thus, see the equation shown.
Example 4.16. Prove Thomson's theorem. Thomson's theorem. If a collection of surfaces are fixed in position and a given total charge is placed on each surface, then the electrostatic energy of the system is at a minimum when the charges adjust so that every surface is in equipotential, e.g., as if each surface were a conductor. The electrostatic energy is given by U equals 1 over 8 pi the integral over V of the absolute value of E squared dV, where the volume is the space between the conductors. Thus, see the next equation. See the equation shown. And delta U equals 0 when each of the phi sub I is constant on the surface S sub I, because then we have. See the next equation. Since delta E equals 0 at surfaces if phi sub I are constant on the surfaces,